Hi everyone, my name is Ebers. I'm a postdoc in the applied math department at UW here, and I'm really excited to talk with you guys today about this idea of data expansion, how to improve the accuracy and availability of the digital biomarkers that we want to monitor for human health and performance. And I'm coming from kind of a dynamical systems data engineering background when I approach my research. And so dynamic systems can be found all around us when we want to study and monitor and control our systems of interest, but they can often present really complex and rich challenges. Dynamical modeling gives us a mathematical framework to describe the world around us, how things behave and change and evolve in time and space. And this modeling allows us to quantify these rich interactions between these quantities that co-evolve and what we want to study. However, complex systems can be really difficult to measure. Imagine trying to measure the sea surface temperature at every single location across the entire globe. That's just infeasible. And the physics-based modeling underlying a lot of these dynamics is just really not readily available. And because of this, we want to use state estimation. But these high-dimensional systems are really hard to estimate the state. And so we want to try to exploit the low-rank structure or the patterns that kind of underlie a lot of this behavior. So how do you know where to measure to best capture these patterns? That's actually a grand challenge in optimal sensor placement. And so if we want to do a model-free state estimation, the folks that are doing that currently only utilize the current value of the system at one time location, or at the single point in time that you're measuring, rather than conditioning upon the time history of the sensor measurements. So instead, what I'm theorizing is that we can use the time histories of the sensors themselves to encode global information about the measured high-dimensional system. And we accomplish this by using shallow recurrent decoder networks. We like to refer to this as SHRED. This got a little messed up, sorry. The goal of SHRED is to learn a mapping from a sparse set of measurements of the trajectories or sequences, time histories, same thing, and map that up to the high-dimensional state space. This does require us to have the full data set of the sensor trajectories in order to train the SHRED model. So this is a supervised machine learning method. But if you don't have access to the high-dimensional data set, you can often use a proxy like a surrogate or simulation data. And so the first part of SHRED is basically just an LSTM. Any sort of recurrent neural network would probably work. But this processes a time delay embedded representation of our time histories. And this step is learning a latent representation of this sparse dynamics over time. And then what happens is our feed-forward neural network acts as a decoder to reconstruct that high-dimensional state space from the sparse temporal latent space. And the theoretical underpinnings of SHRED is based upon the idea of separation of variables, which is a technique for solving linear partial differential equations. And I want to talk about this. So understanding the mathematical theory that underlies machine learning is often really important, especially for facilitating the interpretability of our results, understanding why and how things can break, the limitations of their uses, and also just to dispel this idea that machine learning algorithms are just black boxes or magic. So how many of you guys have taken a differential equations class or know what differential equations are? A lot of you guys, awesome. So if you haven't, at its core, differential equations is just telling us how a system changes. And two of the most basic types of differential equations are ordinary and partial. Ordinary differential equations, or ODEs, are just a function of one independent variable, like time. And partial differential equations are, or PDEs, depend on multiple independent variables like time and space. So to build intuition, let's just take a look at one of the simplest PDEs we can study, the single dimension heat equation. So here, our heat equation accounts for the fact that temperature changes both in space and time. So if we look at when time is 0, our temperature is distributed across space as such. And as time evolves, so does the temperature across space, so on and so forth. And what you may notice is that each square, or state, is affected by its neighboring square. Okay, we have a dead battery. I'm just going to talk really loud. Therefore, a local spatial position is coupled to its neighboring position, and by extension, is ultimately coupled globally due to spatial derivatives. A standard method for solving PDEs, specifically linear PDEs, is the separation of variables, like I mentioned. So separation of variables assumes that a solution to this linear PDE can be separated into its product of its independent variables, such that we can split this up into a product of its space and time, in this case. And this solution form is then used to reduce, whatever PDE we're studying, but in this case, the 1D heat equation, into two much easier to solve ordinary differential equations. And we hypothesize that shred is like this data-driven separation of variables. We theorize that the LSTM is learning what the dynamical system is doing in time, and the shallow decoder is learning what the system is doing in space. So how does this connect to human health and performance? So during my PhD at UW, my research focused on using machine learning to understand and enable human mobility. I spent a lot of time thinking about how to quantify human movement, such as with motion sensing. And motion sensing and analysis is essential for monitoring disease progression, guiding rehabilitation treatment, evaluating sports performance, and informing assistive device design, among many other things. Biomechanists collect a lot of data, but different environments are going to dictate what sensors can be used. And a lot of important biomarkers of health or performance can be measured with technologies available in a laboratory setting. So for example, biomechanists traditionally characterize motion, such as gait or walking, by measuring biomechanical variables like your joint kinematics, your kinetics or forces, and spatio-temporal parameters like your step width or step length. Certain biomechanical variables have been established as biomarkers that correlate with meaningful health outcomes or performance outcomes, such as your knee adduction angle for your propensity to ACL injury, or your step width variability for fall risk, for example, in aging populations. However, life is not lived in a clinic. More portable devices offer opportunities for out-of-lab motion sensing. Understandably, these types of sensors tend to be more limited in what they can measure about human motion relative to the state-of-the-art laboratory setups. But portable devices like smartwatches have immense promise for this natural environment tracking. However, this data must be linked to the meaningful biomarkers to provide actionable insight for this monitoring, diagnosing, and treating mobility-related health and performance issues. And therefore, my research goal was to use shred for this idea of data expansion or reconstruction or inference to improve the accuracy and availability of our digital biomarkers for monitoring human health and performance. So, kind of an overview of what my thinking is if we have on the left a limited sensor measurements capable of kind of estimating our metrics of interest in the wild, at home, in the community, and then we can measure a comprehensive data set in a laboratory setting. My hypothesis is that we can learn a mapping from this sparse set of wearable sensors to a more comprehensive set of human movement measurements. And hopefully, with this expanded data set, our estimation of the digital biomarkers will improve our accuracy and availability agnostic to the environment. However, before we can monitor these biomarkers robustly, we need to understand if and how well we can map between our wearable sensors and our laboratory measurements. Therefore, we evaluate the performance of shred for a variety of different of movements, including controlled movements like treadmill walking and running, or more exploratory things like gait pattern exploration, or unconstrained activities like acting or freestyle dancing. So the first data set we evaluated was the most simple example that we could think of. We used a data set that collected marker-based data quantifying your joint kinematics, which are your joint angles over time, during treadmill walking for 12 non-disabled individuals. We trained a shred model to reconstruct the full configuration of kinematic measurements, which were, I think, 20, using just either 1 or 3 markers. And we compared how accurate shred was compared to 2 other models. One is just a shallow decoder, which is shred without the time histories, and then just a linear model. And while there's a lot to unpack here, the takeaway that I want you to notice is the scale of the y-axis on each of the box plots. So shred in blue has by far the lowest reconstruction error. And that's really all we're looking at. It's just comparisons of reconstruction error at this point. But if we want to look at the actual trajectories and reconstructions from this example for just one of the individuals, we see a very good time series reconstruction. And this is a good gut check, especially for using experimental data, because this data was collected from non-disabled adults walking on a treadmill. The dynamics are going to be very rhythmic. And if shred cannot succeed in reconstructing this, it is most likely going to struggle with expanding to other movement tasks that are much more complicated. So to kind of up the ante, we wanted to see if we could reconstruct inertial measurement units, or IMUs, and their signals worn at the chest, pelvis, and ankles, just using IMUs at the wrists, like what is in your smartwatch. So IMU sensors can monitor things like acceleration, orientation, angular rates, and other gravitational forces about the body segments that they're attached to. So it's quantifying the motion of your body. So data were collected from 10 non-disabled adults, again walking on a treadmill. And we just used violin plots to capture an aggregate distribution of our reconstruction errors across individuals and across all 36 signals. It's a very, very high-level summary. But again, shred, denoted in blue on the right, accurately reconstructs the full configuration of IMU time series signals. So to get into more exploratory movements, we wanted to investigate more complex or unusual movement patterns. So we evaluated how well shred could reconstruct motion during gait pattern exploration. How many of you are familiar with Monty Python's Ministry of Silly Walks? Yeah, so imagine a data set where the researcher asks folks to walk on a treadmill in as imaginative or as silly walks as you can come up with. And while this data collection was originally used to understand if people could voluntarily modulate their motor control, or how you coordinate your muscles, it provided a really interesting data set to test this idea of data expansion. And we wanted to kind of understand this idea between motion complexity and data expansion accuracy. For example, if a shred model is trained using data sets that were quantified as more complex, will it have a better reconstruction accuracy than a data set that was deemed as less complex? So let's just look at subject 2, for example. When we compare a shred model trained on increasingly more complex data, listed on the y-axis from left to right, starting with just a baseline walking trial, and as we add more and more complex gait patterns, when we reconstruct their full set of kinematics, we observe low error across the board. This is really exciting, very good gut check. What's maybe more interesting is when we see how well these models can predict the kinematics of unseen or new exploratory walking patterns. And we notice that models trained with more complex exploratory movements on the right have lower prediction error. And if we looked at the impact of motion complexity for a different individual, we see a relatively similar story. However, we notice that the variability in predicting the new exploration movements from person to person. So looking at subject 2's shred model, trained on baseline walking, predicting less complex exploration, that has a much higher error than subject 14's results. And this is basically a reminder that when we're trying to do personalized human movement sensing, we need to understand what is relevant training data for robust and reliable data expansion. This brings me to my final data set. Continuing on my quest to understand the relationship between motion complexity and data expansion accuracy, instead of the complexity stemming solely from unusual movements, we added the complexity of monitoring motion in a free moving space, so not just constraining folks to walking on a treadmill. So this data set, the total capture data set, it's a benchmark data set used often in computer vision. And it's very obvious that it was. It's definitely not created by biomechanists. There's some interesting things in the data that made this analysis very tricky. But this data collection, 5 individuals were asked to perform tasks like walking, acting, freestyle dancing, all in this kind of unconstrained environment. And if we look at the effect of training personalized shred models with either the most complex movement tasks or just randomly chosen ones, it's a bit of a mixed bag. For some people, the more complex tasks created more accurate representations. But for other random tasks, created the better reconstructions. So I don't know if you guys can see subject 1 in red. They had a lower reconstruction error with the complex reconstruction. However, with subject 5 in orange, they had a lower reconstruction error with random. So I alluded to this, but I think part of this is just due to inter-individual variability. So when I watched the videos back and monitored what the individuals were actually doing, I noticed that with a lot of these movements like acting and dancing, there's a lot more upper body movement and people just kind of staying stationary with their lower extremity. And if you remember, I'm trying to reconstruct lower extremity movement. So that's not super relevant to this task. So combined with the small sample size of only 5 people, we really can't conclude anything yet about the influence of motion complexity with environment exploration. But again, this really highlights the limitations of motion inference and reinforces the importance of relevant training data for this robust and reliable data expansion. And in this case, we likely need more data. So in summary, shallow recurrent decoder networks can expand human motion data by mapping a sparse set of sensor measurements to this dense set. However, motion complexity and more data should be incorporated during the training of these motion inference maps to increase robustness towards reconstruction. And this data expansion is a really exciting step towards improving our accuracy and availability of digital biomarkers for human health and performance. So with that, I kind of sped through that, so I'm happy to talk a lot more about this, but thank you for listening.
Questions, anybody? I'm sorry, mic isn't working, you have to be a little loud.
Yeah.
Susan, great talk. I was wondering, in terms of training data, if you've looked at the ballet or any videos of ballet dancers, they do a lot of lower body movement. There's thousands of hours of that data.
Yeah, I haven't, mostly because a lot of the application areas of this are for like monitoring clinical populations. And so utilizing training of like for dancer training or dancing movements for training data isn't the most applicable for trying to create a robust distribution essentially of tasks that an individual might be doing during their day-to-day.
And second question, on the previous slide, I was wondering what the minimum amount of data required for the biomedical test, if you go to the previous slide.
We can't. Oh, I'm including their own one, I'm so sorry.
Yeah, and the motion capture laboratory, I'm just curious to know what is, because they're capturing so much information, but do you need all of that, right? You could probably take a subset of that. So is Shred trying to imitate the intent, recapture all of it, or is it more effective to just say, okay, we actually only need 20% to be able to make the predictions, we should just try and recapture them?
Yeah, there's actually me and another one of the PhD students in the room. We're actually trying to understand like what data is relevant, how much, if we can decrease the amount of training data needed in by maybe supplementing it with more exploratory patterns. So in you know, the cop-up answer is it depends. I think part of it depends on what it's actually measuring. This is going to fail as soon as you start adding in a lot of like reactivity. If you're like changing direction, and it's not included in the distribution of the training data. So I think a lot of it has to do with what are you trying to reconstruct and how accurate do you want it to be across a spectrum of movements. It's great at steady state, which could be really applicable for like at-home, you know, treadmill training for folks who need to do physical therapy, and do that not in a lab, not have to physically come in the lab. But if we want to more robustly do that across a lot of different activities in a like semi-supervised learning way, I think there's going to have to be a classification of the task first, and then a reconstruction within the task. So a lot of the data has to do with or a lot of the amount of data and the type of data has to do with where do you want it to be deployable.
Thank you.
Yeah, so your task mainly focus on reconstruction, but have you tried using this is similar, reminding me of an autoencoder. Have you tried to use the bottleneck, the complex representation, and try downstream task classification with some labels and stuff like that?
I mean, this is an autoencoder like structure. So are you talking more about like forecasting or
Like something to do more with clinical behavior, clinical outcome?
mm-hmm.
Specifically biomarkers that are related to clinical.
Yeah, so one of the things that I'm evaluating right now actually is trying to see if I can better predict fall risk with folks who have multiple sclerosis. So than just like the traditional sparse modeling. So a lot of these folks, I think there were 38 adults with multiple sclerosis came in for 4 in-lab sessions every 6 months over 2 years. So they do a big comprehensive, I think there's 11 different IMU sensors, that's the dense configuration. For the 48 hours after they visit the lab, they are given 2 IMU sensors placed by clinicians, and then that's monitored continuously afterwards. So this seems like a really interesting data set to do that mapping and see how well we actually can reconstruct the rest of the comprehensive lab.
Yeah, but my point is that instead of needing to reconstruct it, maybe there's already enough information if you train the model on the dense set and then you somehow were able to incorporate the sparse set, maybe just the dense set representation and some of the sparse set together can predict the fall risk or whatever clinical factor of interest.
Yeah, currently a lot of the sparse sensor sets aren't able to robustly monitor those things, and so, for example, biomarker of fall risk. For example, your Apple Watch tries to detect when a fall happens.
Right.
This is trying to predict if they are at risk of it.
Yeah.
And so I think the distinction there being one of the biomarkers we're trying to monitor with this is step width and step length variability. And you really can't monitor that without being in a motion capture lab, and that's a higher fidelity measurement modality for anticipating the risk rather than when it happens. Because an accelerometer is going to be able to
So
capture
you're
that.
trying to use the sparse set to impute the dense set, which then can act as a predictor.
Yes,
Okay.
yeah, exactly. The idea being if you have more information, you would calculate that normally in a lab, but you can't calculate that like at home. So can you kind of bridge the gap so you can do that anyway? Yeah.
Yeah, exactly. So I assume you're trying to reconstruct the data from the other sensors using the wrist data because Apple Watches are a common thing that people have.
Yeah.
But have you also looked at seeing how well, if you like just choose one sensor and try to reconstruct the others, like which one is most informative towards the reconstructions? And then like in an ideal situation, would you use that to inform kind of like the lab, which sensor to send to people?
Yeah, we did a pretty robust sweep, but I don't have the slide in here. We did try to look at sensor location influence on reconstruction accuracy. For walking, it doesn't really matter. One of the results that McKinsey found is that for running, so a more dynamic task, it can sometimes matter depending on what you care about. But for the most part, all of the agnostic to sensor location, you're going to have a robust reconstruction accuracy. That being said, if you care more about what's happening at the ankle, maybe put the sensor there in the first place so you know you have high confidence in that. If your biomarker has more to do with something, for example, at the pelvis or the chest, maybe put it there so you have a lot more confidence in that. These are going to be, have their pitfalls